Hello, everybody, and welcome back to BioSC 140 Human Physiology. This video is going to cover Laboratory 21, Cardiovascular Physiology Lab. This is on Lab Quiz 3 material. So, as with many of our labs, there are a few different components of this overall Lab 21. So the first one I've actually mentioned before in this class in past lectures. It is the microcirculation of the goldfish tail demonstration. Next up, we're going to do a part out of the supplement Lab 21 section on venous pressure. Then we're going to jump over to FOX 7.6 for arterial blood pressure. And then we're going to have a worksheet, some homework on Starling's forces. See the explanation and questions in the supplement. So let's move on. Goldfish circulation. All right, so we do this for a few reasons. When we're studying the circulatory system, it's kind of hard to visualize. I mean, it's like we kind of conceptually understand, all right, there's this liquid flowing through our bodies with cells in it and everything else we discussed in the blood lecture. But when you actually see it, it changes your view on it. It changes kind of how you process it. And so what we do in lab is we have a live goldfish, and I get to play anesthesiologist, and I get to put it to sleep for a little bit. I'm 100% right now with waking the fish up, so don't worry. We put the fish to sleep, and then we put the fish in a petri dish with some water, and we put the tail on a stack of microscope slides. And then we slide that underneath a microscope that's connected to a television at the front of the room. And so students can actually see individual red blood cells flowing through veins and capillaries and arteries. Students can actually see in live time, in real time, blood flowing through arteries and veins and capillaries, and it's really, really, really cool. It's one of those labs. Students do this for most labs, but there's probably more students that do it for this lab and the frog lab and a few others. They make Instagrams. I don't know what they're doing, but they have their cameras out and they're making stories or something and taking photos. A ton of students always do that for this lab. So it's really, really cool. We're not live, we're on the internet. So we're not going to do this experiment. We're not going to do this demonstration together, but I have posted videos of it going on, of a video of it from YouTube. And you can also, search for Goldfish Circulation videos, and you can see it on YouTube. But it's the video that I posted. It looked kind of like these two right here. It's awesome. So enjoy. Part B, venous pressure. So things flow from high pressure to low pressure. In our aorta, we have high pressure. In our venous system, we have low pressure. In our right atrium, our left atrium, we have low pressure. And so things flow from high pressure to low pressure. And our body needs to maintain this pressure gradient. This is kind of jumping ahead a little bit, but our heart, the ventricles push blood into their corresponding arteries. That increases the pressure in the corresponding arteries just outside of the heart. And as the blood moves through the circulatory system, it loses pressure because of resistance. It's the resistance. The further it moves through the circulatory system, the more resistance it comes across, the lower the pressure is going to be. So high pressure, right where The ventricles pump the blood out into the arteries. Pressure grows down gradually in the arterial system, throughout the capillaries, and throughout the venous system. So we're going to explore the venous pressure, the pressure of our veins. So procedure, stand next to the chalkboard and mark the height of your right atrium. So we have students stand with their back to the chalkboard. We then mark the height of their armpit, assuming that the height of their armpit is the height of their right atrium. RA stands for right atrium. You then hold your hand at your side below the level of the heart, and blood will pool into your hands due to gravity, and your veins are going to distend. Here you can see how the veins are distended in this person's hand. This lab you can actually do at home, so I want to encourage you to give this a shot at home. Don't get in trouble for writing on your parents' wall. Use tape to mark the height of your armpit or something like that. So hold your hand down by your side and see how gravity pulls the blood down into your veins, and it kind of pools and causes your veins to extend or swell. Then raise your right hand slowly. And once it gets above the heart, gravity is going to start to aid the blood to move back to your heart. When your hand's below your heart, gravity's kind of, preventing it. Or not completely preventing it, but it's adding it's pulling in the wrong direction, right? And once your hand gets above your heart, gravity's going to start pulling in the right direction. Gravity's going to aid venous flow back down to your heart. I want you to mark the level where your veins collapse. Usually a little bit, when in discussion we'll get into the exact amount, but there's going to be a point where your hand is above your heart, above your armpit, where these veins are going to go flat, like they are in this photo. That's the level where you mark again. So you mark the armpit, and then you mark the height of your hand when the veins collapse. That's your other marker. So 2 marks, one at the height of the armpit, one at the height where your veins collapse. And it's the difference between those two that allows you to calculate the pressure in your veins. The veins are going to collapse when the pressure in your veins is greater than the pressure in your atria. So pressure in your veins is greater than your pressure in your atria. Remember what I talked about? Things go from high pressure to low pressure. So when you have higher pressure in your veins and your atria, blood's going to flow in. So measure the distance of height from the right atrium to where the veins collapse in millimeters. So measure that distance in millimeters. That's important. Sometimes I put it in centimeters, or sometimes students calculate in centimeters. And then when they do the calculation, they don't get a good answer. And it's because it's in centimeters. Make sure you want it in millimeters. This corresponds to a venous pressure of blank millimeters per minute. So divide this number, the number that you get in millimeters, the difference between right atrium and where your veins collapse, divide that by 13.6, and you'll get the pressure of your venous system. So venous pressure is equal to VC, that's venous collapse, minus right atrium. So these measurements are from the floor. So from the floor to where your venous collapses, and then from the floor to your right atrium. So really it's the difference between those two, divided by 13.6. So make sure it's in millimeters. Normal range is 4 to 10 millimeters per mercury. Make sure you know this number, normal range for the quiz. All right, moving on to arterial blood pressure. All right, so this is going to take a little bit of explaining. There's going to be a little bit of discussion that comes into this experimental procedures video, but that's good. It's review, it's repetition, it's going to help you learn. All right, so arteries have higher pressure. Blood flows through your arteries, it flows into your capillaries and your veins. We need higher pressure in your arteries. We've all seen this before. We've all seen the sphygmomanometer before, the blood pressure cuff before. We're going to learn and we're going to talk about how to use it and about why it works. What's the process? What's the thought process behind it? So I'm going to start someplace a little I'm going to tie this all in. So just a heads up, I'm going to tie this all in. So has anybody ever been by a stream that's slow moving? So a slow moving river, like a lot of my family lives by the Mississippi River. The Mississippi River is really, really wide, and it kind of just flows very smoothly along. Like the top of the water is very, very smooth. If anybody's been to the Delta, the water it's moving, but it's moving very, very smoothly. The top of the water looks like glass if there's no boats or anybody playing in it. It's very smooth. The Mississippi River, it doesn't make noise. It's not loud. Compare that with some of the mountain streams that we have in California. Oh, the smooth river, you could also think the Sacramento River in Sacramento. It's not a loud river, it's smooth. Compare that with some of the mountain streams we have in California, some of those mountain creeks. A mountain stream with lots of rocks in it that causes the water to bounce all over the place and shake all over the place. Moose! All right, Moose is interrupting. So when the water is moving in the Mississippi River, in the American River in Sacramento, it's moving straight, it's moving smoothly. There's nothing, it's like this picture right here. The blood is able to move straight through. This picture right here where my marker is. The water's moving straight through. It's got what we call laminar flow. It doesn't make a lot of noise. When you have a mountain stream with a bunch of rocks in it and it's making a lot of noise, you have turbulent flow. You don't have laminar flow, you have turbulent flow like right in this picture. There's water bouncing all over the place and it makes a lot of noise. In your bloodstream, normally you have laminar flow. You have blood that's flowing straight. There's not a lot of eddies or there's not a lot of chaos. It's just flowing straight. And it's usually pretty silent. What we're going to do is we're going to use that knowledge to figure out our arterial blood pressure. So turbulent blood flow creates noise. Laminar blood flow does not create noise. That's what I was going there with there. Okay, so in order to use a sphygmomanometer, a blood pressure cuff, we're going to put the blood pressure cuff on our patient. We're going to put the stethoscope on their arm, and we're going to pump the cuff up to 160 millimeters of mercury. So what's the typical blood pressure? Textbook 120/80. So we're going to put it above the typical blood pressure. We're going to completely close the brachial artery, completely shut off blood flow to the arm. If there's no river flowing, the river's not going to make noise, right? If there's no blood flowing, the blood's not going to make noise, right? We're then going to slowly release the pressure in the blood pressure cuff, and we're going to listen for a sound. We're going to listen for a sound. And the first sound we hear, we're going to look at the pressure gauge, and we're going to note the pressure at when we hear the first sound. That pressure, that first sound is going to come when, so we have a range in blood pressure, right? 120/80. It's fluctuating between 120 and 80 or wherever that person's blood pressure is. At the high point, like the 120 for if it is 120, at that point, the pressure in the artery is able to overcome the pressure in the cuff. And so some blood is going to flow through. When that blood flows through the blood pressure cuff, it's not going to be laminar, it's going to be turbulent. So it's going to It's going to have eddies in it. It's going to be turbulent flow. We're going to hear it. So at the moment that our artery is able to, that pressure is able to overcome the blood pressure cuff, we're going to start to hear turbulent flow distally to the blood pressure cuff. That's our systolic blood pressure. We're going to keep decreasing the pressure in the cuff until we no longer hear it, until we no longer hear that turbulent flow. At that point, when we no longer hear turbulent flow, we're going to have laminar flow restored. And that's going to occur when the pressure in the cuff is lower than the diastolic blood pressure. So note the pressure on the gauge when you can no longer hear that turbulent flow. When no pressure is heard, that moment corresponds with our diastolic blood pressure, the lower range. So in that typical 80 to 120 range, first sound, systolic, the high pressure, the 120 number. Last time we hear a sound, diastolic, the relaxation phase, the lower pressure. All right, so that's how you take a blood pressure. We're going to talk a little more about this in the discussion. All right, so we have our systolic and our diastolic blood pressures. You're going to say 120 over 80 or whatever that person's is. Right here it says 120 over 70. We're going to calculate a few things. We're going to calculate pulse pressure, or PP. SP stands for systolic, so we're going to take our systolic blood pressure and we're going to minus diastolic blood pressure to calculate pulse pressure. We're then going to calculate mean arterial blood pressure, or MAP. We're going to talk a lot about MAP in this class. So mean arterial blood pressure, or MAP. MAP is equal to 1/3 systolic blood pressure plus 2/3 diastolic pressure, or there's another way to calculate it. Diastolic blood pressure plus 1/3 systolic minus diastolic. You can choose whichever equation's easier for you to use. They'll get you to the same place. In this lab, I want you to calculate, normally we would do this 3 times for everybody in our group, and we'd have a good time practicing this. Then we would move on and we would calculate our MAP while the person is sitting. So have them sit and relax for 2 minutes, calculate their MAP. Stand and calculate their blood pressure immediately after standing, and then calculate their blood pressure after 2 minutes of standing, and then calculate their blood pressure while they're reclining, laying down, or supine. Mean arterial blood pressure measures taken in changes in position or posture. How do you think their MAP is going to change? Their average blood pressure is going to change in these different positions, in these different situations? Hypothesize. All right. So while you're loading the next video, hypothesize. Which one's going to have the highest blood pressure? Which one's going to have the lowest MAP? As always, if there's anything I can do for you, if you have any questions, just let me know. I'm here to help. I will see you in the next video.